So let's see if I can quantify those rules. So the rules for finding, instead of slope, I'm finding the area. Rules for finding an area. Well, what's the first thing I did? Well, the first thing I did was I increased the power of the exponent. So, increase power of exponent. Oh, I should say old exponent. By 1. And that equals the new exponent. That was the first thing I did. And the second thing I did was I divided old coefficient by the new exponent, and that equaled the new coefficient. Right? That's what I did here. So I increased this by 1, and I took the old coefficient and divided by the new exponent, and it worked. So the rules over here are rules for finding the slope. The rules over here are rules for finding the area. So again, going from a position time graph to a velocity time graph, I need to find the slope. So I'd use these rules. For a velocity time graph, if I want to find the acceleration, I would find the slope. So again, I'd use these rules. But if I have a velocity time graph and I want to find the position, that would be the area, I'd have to use the rules over there. In calculus, these rules here, this is a branch of calculus called finding the derivative, or derivation. So this is a whole half of calculus right here. Find the slope. These are the rules for finding the slope, finding the derivative. The other half of calculus, this has two names. Notice it's the opposite of those rules. So sometimes it's called antiderivatives. Not very original. And sometimes it's called integration. Integration means adding up all those little pieces of area. So these are the two sets of rules that we need to be able to do. We have to have them memorized to do what we want to do. Go ahead and stop. Okay, so let's do a little quiz now. For this quiz, you don't have to do any math whatsoever. I'm just testing your conceptual ability. You're given the velocity as a function of time, and I'm asking you, if you're given that function, how would you figure out the position as a function of time? Would you find the area of that, or would you find the slope of that? And same for the next one, and the next one, and the next one. So what I'd like you to do right now is hit pause, and then solve those. Okay, for the second quiz, instead of using the words slope and area, we're going to do the same thing with the calculus words, derivative and antiderivative. So if you're given the velocity as a function of time, this equation right here, and I'm asking you to find the position as a function of time, would you take the derivative or antiderivative? Whatever one, go ahead and put it in the blank. Same thing for the next ones as well. So what I'd like you to do now is hit pause and go ahead and solve these. Okay, the third quiz. What I'd like you to do for this third quiz is I would like you to actually use those rules of calculus we just found for finding the slope, for finding the area, called derivation and integration. And I would like you to actually, given the velocity time graph, go ahead and tell us what that function is for the position time graph, and same for the other ones. So if you could please go ahead and hit pause and do that. Okay, so now let's go ahead and look at the solutions. If you're given a velocity time graph, or if you're given this velocity as a function of time, and I want to find the position, well, I know that the area of this graph gives me position. So the first answer would be area. That's also the antiderivative. And so if I take the antiderivative of that, that would be the second set of rules I just learned. I need to increase the power by 1, so it becomes the sixth power. And I take the old coefficient and divide by that new power. For the next one, I have the position time graph, and I want to find velocity time as a function of time. Well, that would be the slope of this graph. And the slope of this graph is the same thing as finding the derivative. Using the rules for derivation that we first came up with, we have to bring down the power of the variable. Well, notice there isn't a variable here, but I could. I could put t to the 0 power here. So that would be breaking down the 0. 3 times 0, that's going to give me 0. Now, we knew that already because this says the position doesn't change with a function of time. It's constant. That means it's not moving. The velocity is 0. For the next one, we're given the velocity as a function of time, and I want to find the acceleration. Well, I know that the slope of the velocity time graph gives me the acceleration, also called the derivative. So, following the rules for derivation, I take 7 times the old exponent, and I get 21, and decrease the exponent by 1. So it's 21t squared. And then lastly, for the last one, I have the acceleration as a function of time, and I want to find the velocity. I know that the area bounded by the acceleration time graph gives me the velocity. So that is called anti-derivations that I have to do. So I have to follow that second set of rules. So I'm going to increase the power by 1. If it was -2, add 1, it becomes -1. And I have to take the old coefficient and divide by the new power. 2 divided by -1 is -2. Okay, I'd like you to try one more quiz problem here. We're given the velocity as a function of time as being 3t squared plus 4. And I would like you to pause here in a second and figure out what the position as a function of time is and what the acceleration as a function of time is. So go ahead and hit pause. Okay, so let's go ahead and solve this. Now, this one's kind of interesting because if I want to find the acceleration, that's the first set of rules because the slope of the velocity time graph gives me acceleration. So that's finding the derivative. It's going to be 3 times the old power, which would be 6. T to the 1 less power, 2 minus 1 is 1. So I just won't put anything there. It's the same thing as 1. This one doesn't have a t with it, but I could put a t to the 0 power. If I bring down to 0, 4 times 0 is 0. So that's it. That's the answer right there. Acceleration as a function of time is equal to 6t. Now, if I want to find the position as a function of time, I don't want to take the derivative of this because that would be slope. That's not right. I want to take the area, which is the antiderivative. So I need to increase the power by 1, so it becomes t cubed. And I have to divide the old coefficient by that new power. So 3 divided by the cubed, 3 divided by 3 is 1. So I just won't put anything there. It's known to be 1. Now, you might be thinking I could stop there, but you can't because, remember, this is t to the 0 power. I've got to increase that power by 1, so it's going to be t to the first power now. And I have to take my old coefficient and divide by that new power of 1, so it's 4 divided by 1, which is 4. Now, 4t to the first is the same thing as just simply 4t. So my position as a function of time is t cubed plus 4t.